a human hand, the wing of a bat, our eye, the 800-lensed eye in a fly. Life has evolved incredible variations, sizes, and shapes. Now scientists are discovering that despite the differences, animals are related in totally unexpected ways.
That's really remarkable, that a version of the same recipe can build bodies that are so utterly different.
In the midst of developing a video game based on evolution, game designer Will Wright is investigating a toolkit of genes critical to how evolution works.
It's interesting that something as versatile as a human hand could actually be coming from something as simple as a fin.
It's transforming our view of evolution and our understanding of how we came to be. What starts as just a single cell somehow becomes a trillion-celled human being. How did we come by this exquisitely constructed form?
Why is your heart on the left and not the right? Why is your thumb different from your little finger? Why is your arm different from your leg?
From all the parts in Mother Nature's garage, how did our prized parts come to be? Upright striding skeleton, nimble hands, powerhouse heart muscle, naked skin, clever brain. The latest science is taking us into our family tree as never before, revealing a story that connects us with some of the most unexpected creatures in the animal kingdom. How did so many experiments in bodybuilding over so many millions of years ultimately fit together a body such as ours? Huge question. But we're getting some unexpected help from video game designer Will Wright. He revolutionized the game industry with SimCity and The Sims. Remarkable simulations of cities and the lives of their residents that parallel the real world. Now, he and his team are hard at work on a new challenge. One of the most ambitious games ever, simulating the process of evolution. It's called Spore, and in it, a player designs creatures that must compete against predators, mate, obtain better body parts, and if they survive, ultimately become spacefaring voyagers. Replicating evolution's creature making has led Will Wright to develop an interest in how evolution actually makes bodies and changes them.
I'd really like to kind of go out and see how nature does it. What are the things that evolution has at its disposal to define a creature, to mix and match the parts, and eventually come up with a unique organism that's going to go out there and have to live its life and try to reproduce.
To find out, Will Wright is going to visit top scientists exploring the connections between evolution and genetics. Answers first turned up in a bug. You wouldn't think that anything with antennae, wings, 6 legs, bug eyes, and a taste for decaying fruit could share a resemblance with us. But you would be wrong. Will Wright is at UC Berkeley's Fly Lab. It may be tiny, but the fruit fly is the giant of genetics. No organism has been studied more thoroughly.
So what's with all the flies?
Well, you know, these are normal flies. These are what we call the wild type. We also have some very interesting mutants that I think you'll find quite compelling.
Geneticist Michael Levine is a key figure in a new science called Evo-Devo that's found a doorway into evolution by examining how an embryo develops into an animal. Sometimes that process can go very wrong.
So, well, that's a huge blow-up of a fly head.
Okay.
Do you see anything a little peculiar about it?
Yeah, the antenna look very strange. What's with that?
This is a mutant called Antennapedia.
So that's a leg on the left side?
That's a leg, not just on the left side, but on the right side as well. Both
Okay.
of those are completely, perfectly sculpted legs. They're wired into the brain like legs. That mutant fly dies in its food because it's trying to walk on its head.
So it
that
has
is
legs where its antenna should be.
Absolutely. That's
And
exactly right.
how does that happen?
How it happens, the reason why a fly turns into a monster, led Evo Devo scientists to discover something truly remarkable about how genes build bodies. Within every living creature on Earth is a complete set of genes for body making. Genes are short sections of the vast DNA code. But recently, something amazingly simple and fundamental turned up. Among the tens of thousands of genes that make things in the body, there's another kind of gene. A gene that tells other genes what to do. A master switch, organizing the highly complex operation of making a body. Even a fly's.
When this mutant came along, I realized 30 years ago, this was the thing to work on. And I knew then those were the genes to get, that those had some very, deep secrets about basic processes of laying out a body plan and controlling embryonic development.
This mutation led scientists to the identity of 8 master toolkit genes, called Hox genes. There are some 14,000 genes that go on to build a fly, but the process starts with the toolkit. These toolkit genes tell other genes where to put the head, the tail, all the limbs, and antennae. A problem in one of these genes during development can transform a creature into a catastrophe.
That alteration you see, the transformation of antennae into legs, that's what happens when the normal gene is put in the wrong place.
Oh, so it's misplacing that part of the fly body to a different spot.
Exactly. Tinker toys.
Okay, so these are like little building blocks that control different parts of the body.
That's exactly right.
Tinker toys, building blocks, Lincoln logs? Could the engineering behind a fly really come down to a handful of control genes? A toolbox for building life? And it gets even stranger.
For years we thought, all right, great, we're working on this obscure little problem that may solve aspects of how you build a fruit fly.
Okay.
But what does it have to do with people? Well, it turns out that related genes are present in our very own genomes, and they're important for our development as a fetus.
Another discovery. Toolkit genes don't just exist in flies. They're in a huge variety of animals, including humans. That's why there is such similarity in the embryos of a fly, a mouse, an elephant, and a human, despite how different they'll look as adults.
A similar kind of recipe underlies the development of bodies as different as those of sea anemones and humans. I mean, that's really remarkable, that a version of the same recipe can build bodies that are so utterly different.
The finished product may vary. Fins, feathers, or fingers. But like distinctive cars, underneath the paint job, the genetic chassis is the same. It's a new way to look at nature's bodybuilding. As if there's a tool shop inside each of us, using a similar set of genes to make parts and appendages in very different organisms.
So these genetic toolkits are like the Legos. And you could make a house out of Legos, or you could make a car out of Legos. You don't need a different type of Lego to make a car.
The discovery of a shared genetic toolkit points to a deep kinship between different species. Powerful new evidence for one of Darwin's most important ideas, the descent of all animals from a common ancestor. But it raises a problem that Evo Devo must solve as well.
There was every expectation that we humans had the most genes. We had 100,000 genes. We would have genes that a lowly fruit fly or a sea squirt would know nothing about. But this is not true. All animals have a very similar set of basic genes, and yet we're so different. So how do you explain that? What's the answer?
The answer to this mystery will take Will Wright back to the beginnings of the toolkit, to some of the earliest moments in creature making, and to one of the strangest ancestors we have on the evolutionary tree. Nothing can match evolution's awesome power for creating creatures. While designing a new game that simulates evolution, Will Wright is investigating what the latest science has uncovered about evolution's creature making. A toolkit of genes that shapes the intricate details of size, structure, pattern, and parts in all animals. How did the toolkit get set in motion in the first place? To find out, Will Wright is retracing its steps. From our present-day body design, we're headed to one of its earliest defining moments, when the toolkit was deployed in our earliest ancestor, a worm. The Earth has gone through a number of particularly intense bouts of creature making, but none as forceful as a time some 530 million years or so ago. It's known as the Cambrian explosion. A burst of animal forms appeared, the ancient ancestors of virtually all the animals that swim, fly, and crawl today. Is this the moment when the toolkit took off?
What's that?
Oh, it's a carnivorous terror bird from South America. But I actually have something a lot older to show you.
Okay.
Will Wright is visiting paleontologist Neil Shubin to find out how toolkit genes played a role in expanding evolution's creativity.
So here's where creature making went crazy. I mean, back about 530 or so million years ago. You know, you see just a blizzard of diversity of creatures coming about.
This is the Cambrian explosion?
Exactly, yeah, exactly. You start before the Cambrian, at about 600 million years ago, with creatures like this. Doesn't look like much, it's just a disk.
Okay.
By about 50 million years later, you find bodies of all kinds. Bodies with all different sorts of appendages, antennae and limbs and so forth.
The Cambrian was evolution's big bang. But were toolkit genes the trigger? It may not be that simple. Toolkit genes were probably building simple organisms before the Cambrian, so this potential somehow remained unrealized. Also, there may have been environmental causes. Ancient land masses were changing, riven by inland seas and lakes, expanding ecological niches for animals to differentiate. Perhaps a changing environment pushed the pre-existing genetic toolkit into high gear.
At some point, you got the tools together where all of a sudden there was a quantum leap in the ability to suddenly make new types of bodies.
And among all the new types of bodies, our branch of the tree started too.
So this is one of our oldest ancestors.
Well, it's related to it. And in fact, you know, it shows the basic body plan that we have today. It has a nerve cord that runs along the top of the body. It even has gill slits. This little worm contains a piece of our own, essential parts of our own body. And it appeared about 530 million years ago.
Eons ago, an ancient worm launched our basic body plan. And it would become a predominant way of making bodies. Symmetrical and streamlined, bilateral, and laid out head to tail. Today, most of the animal life on the planet, including humans, is built on this same bilateral design. It's perfect for mobility. Over time, it's given rise to a huge range of successful survivors. And the genetic toolkit has traveled up the evolutionary tree with them.
Let me pull this back downward toward the ground.
For the Spore evolution game, developers soon realized that making creatures bilateral, identical on either side, needed to be hardwired.
That's one of those things that I think you kind of take for granted, the fact that, you know, all the legs have to move the same distance, no matter how long they are.
Early product testing showed that despite the wild designs players would make, bilateral patterning was almost always a given. Evolution's ancient genetic toolkit laid out a basic bilateral body. Then, a further step expanded the potential for generating new kinds of bodies: segmentation. Will Wright is at another Evo-Devo lab to see toolkit genes in action.
So we want to understand how this incredible, wonderful diversity is generated, what makes these animals different from one another. But to do that, we have to understand how the basic body plan of all of these things is set up.
They all use the same tricks to create this diversity.
Exactly. What we've discovered is that there's the same sort of toolkit of genes that's always used to make the animal.
Once again, the fruit fly is the preferred specimen. Its embryos are obliging to geneticists like Nipam Patel, eager to pop open the hood and check out how it's really built inside.
So we've designed this so that we've been able to detect where the gene is on. What you're going to see is stripes appear on the embryos.
All right.
There we go.
Ooh.
And we can see now very nicely the repeated pattern of segments. So it's a ladder-like pattern with a rung in each segment.
This is basically his spinal column?
That's right. So the whole body is organized in these very nice repeating segments.
It's the groundbreaking step in forming a fly. Just as they did with the ancient Cambrian ancestor, these genes are organizing the body into top and bottom, front and back. But they are also segmenting it into zones of activity, marking positions for organs, appendages, and limbs.
So you have certain genes that are also telling certain segments to specialize. Is that what's causing the brain to occur at one end?
That's right. So eventually, every one of these segments will actually have a unique property to it.
Whether it's in a fly or a mouse, horse or human, similar genes are laying out a body architecture, and segmentation is the method. It's also a moment when the ancient recipe for building bodies can undergo mutation, allowing for accidental genetic creativity. New shapes can come along from DNA malfunctions, causing a toolkit gene to switch on early or late, or never switch on at all.
So could you potentially turn on 2 or 3 more brains in here if you could modify that gene?
So we could do things like that, so that more of the animal could become brain, for example, or do the reverse, and get rid of the brain and turn it in so that it's identical to the abdomen instead.
So you could actually make a really smart fruit fly at this point.
Well, unfortunately, when you do those things, they die.
Oh, I guess that's not really smart.
A mutation causing a fly with 2 brains might not work outside Hollywood, but subtler changes, say a slightly larger wing or a second set of wings, may have real advantages, and that new design could catch on. Creatures and their body parts aren't invented from scratch. They evolve when their genetic networks are modified by ancient toolkit genes. Evolution of form is a matter of teaching very old genes new tricks.
If you take a look at the difference between a mouse and a cat, the difference is not new types of cells, but change in organization. Somewhere along the line, those instructions were modified, not in a way that scrambled them, but in a way that gave subtle changes to lead to the differences between organisms.
Of course, not every organism can stack up against the environment. The genetic toolkit builds bodies that are, at best, hopeful possibilities. Fossil beds are littered with one-hit wonders, evolutionary experiments that prove to be maladapted dead ends.
Genes propose and the environment decides. That genome is not a static thing. It's constantly roiling around, changing where genes are turned on and off. And whether these new traits that are constantly being pushed out there, whether they're accepted, depends on the environment. That baby is evolution.
Evolution has taken millions of twists and turns. How did toolkit genes that made an ancient worm get reconfigured to eventually make the parts that make us? our hands, our hearts, our upright, naked bodies, and ultimately, the brilliant brain in our heads. Deep inside the job plan that makes each and every animal on Earth, even human ones, is a common toolbox of genes, the hammers and saws of DNA, arriving and departing at just the right stages of development to get the job done. It's as if nature ran a body shop, banging out model after model from knockoff parts. Game inventor Will Wright is wondering how the toolkit played a role in the evolution of key parts of our bodies, like that cool grasping tool at the end of our arms.
So evolution has discovered these toolkit genes that it's using to construct bodies in interesting, novel, but yet very simple ways. So I'm wondering how the human body got to where it is, and the human hand, what stages did it go through to kind of get to where it is today?
In fact, the evolutionary stages that will one day lead to something so versatile as our hand really got going with a fish. For decades, paleontologist Neil Shubin had been searching for a missing link, fossils from the first of our ancestors to walk on land. Then something extraordinary happened.
It was July 2004 in the Arctic. We were digging in the rocks, and one of my colleagues calls out, "Hey guys, what's this?" When I first saw this thing, it was one of the most remarkable experiences of my scientific career.
Shubin had come face to face with a 375-million-year-old intermediary between fish and amphibian, and a piece of our own evolutionary past.
This is an unbelievably special kind of fish. Not every fish had a neck. In fact, this is the first fish that had a neck. This is the first fish that had a wrist.
Shubin and his colleagues named the creature Tiktaalik, a native Arctic word for large freshwater fish.
So if you look at Tiktaalik, what you see is, the upper arm, forearm, and the wrist. I mean, just compare it to my own body. Here's my forearm. Here's the wrist of Tiktaalik. Here's my wrist. Here are the palm bones of Tiktaalik. Here's the palm bone. Here's my own palm bones. And these are pieces of my own body seen all in a fish.
Hands are an extraordinary human tool. Yet within it are component parts modified over millions of years. But why did the change happen here, in this fish, at this time? After traveling from one genetics lab to another, Will Wright can in turn offer Spore's unique visualization tools to a scientist. Using the game's creature creator, Neil Shubin will first try to bring his prehistoric fishapod, Tiktaalik, to life. And then we'll get a sense of the evolutionary forces in play that would one day lead to the human hand.
Let me do a cleaner slate. Let's just take a body.
Grab the arm.
I see something along.
Yeah, there you go.
I am making a Tiktaalik.
Pick the mouth from the second palette on the very top,
There.
yeah.
Okay.
Some are omnivores, some are carnivores.
Okay.
Was Tiktaalik a carnivore?
Yes, very much so. So this one really looks like a Tiktaalik mouth.
What's interesting is when you mutate these genes in the laboratory or through natural mutation, you can actually tweak the body plan of organisms, kind of like what we're doing here to some extent,
Okay, so in this case, the player is playing the role of the gene.
Right.
That's pretty good. There's Tiktaalik head. And let's make it a little longer. Let's make it a little flatter.
It's as if Neil Shubin has a toolkit of genes, and as he works, Tiktaalik takes shape.
What do you want next?
I would love to put some limbs on this thing, or fins.
Is there a limb that looks like a fin?
Yeah, just drag them out
Okay.
until they connect. Yeah. Those would
And
hit
at
all
the
the
end-
bone parts.
Yeah, this
that we
is
have.
kind of really kind of close. It had the bone parts we have.
Okay.
And yet, it didn't have fingers, okay? But
Okay.
it had a fin webbing. So this is sort of approximating that.
It's interesting that something as versatile as the human hand could actually be coming from something seemingly simple as a fin.
Yeah, I know. That's what looking in the distant past shows you. And you find the context for the origin of many structures is utterly different from how they're being used today.
Sounds pretty tough there, doesn't it?
Tiktaalik has arrived.
Yeah.
As with other mutations, genes bring on the change, but the environment determines if the change will survive. 375 million years ago, Tiktaalik swam in rivers filled with fierce predators. Some over 16 feet long, bearing teeth the size of railroad spikes.
If you're living in a fish-eat-fish world, there are three strategies. Get big, because big fish eat little fish. Get armor, because that protects you. Or get out of the way, avoid the fight.
When Tiktaalik changed its fins, a whole new strategy emerged.
And it looks like Tiktaalik was getting out of the way. Because again, if you look at the structure of the fin, this is a thing that's built to do a push-up, to support itself on the ground, either in the bottom of the water or on the mudflats. So this is a creature that was clearly getting away from the fight, if you will.
One small step for fish, one giant leap for life onto land. All that's left is to find out how this change to fin and bone occurs. But for that, the Tiktaalik fossil is missing a key ingredient. It's too old to retain any DNA. In its place, Tiktaalik's closest living relatives, sharks, skates, and paddlefish, can provide Shubin a way to investigate toolkit genes. In the lab, he can tinker with fin mutations to discover how they may have redesigned Tiktaalik. The body of an adult skate is encircled by a pair of majestic pectoral fins. And building fins is exactly what interests Neil Shubin.
Most of the body.
These are mind-blowingly
Isn't it
gorgeous. I mean,
Yeah.
just the structure you see so clearly.
But these are actually the most primitive living animals that have appendages, that have fins.
So we're actually sharing a lot of our toolkit genes with this little guy here.
Yeah, it's remarkable, despite the fact that it's been over 400 million years since we shared a common ancestor with these things. The toolkit genes are largely the same.
Will Wright is getting a first-hand view of a fish hand in the making.
What you're seeing on the top there, in the upper left, is you're seeing the normal dorsal fin of a skate. Now, if you treat the developing skate with a chemical, in this case, like vitamin A, it causes a single gene to be turned on in the wrong place.
All right.
And what you get is the fin on the bottom right there, where you see it has all those bones sticking out. It looks very different.
So that bottom one looks surprisingly like the Tiktaalik fin.
What it's really showing how just changing a single toolkit gene, where it's active, perhaps even when it's active, I mean, that could change the whole anatomy of the fin.
Experiments like these are filling in the pieces to Tiktaalik's story and to our own body's origins. Fortunately for us, a fish developed the means to move on land some 375 million years ago, giving rise to our terrestrial ancestors. What followed were countless design changes. But once on land, there were clear advantages for highly active animals. They needed new body structure, and few were more important than a retooled heart. Energetic bodies, especially ones with large brains, need lots of fuel and oxygen delivered to every cell of the body. This is where a plumbing system with a souped-up pump comes in. Every second or so of every minute, night and day, without fail for your entire life, your heart beats. It has to, or you're dead. The origins of the four-chambered human heart go back more than 500 million years to a simple pulsing tube in an ancient marine filter feeder. This is the moment when toolkit genes added complexity to hearts. Hearts have evolved into so many shapes and forms. Fish have 2 chambers. Amphibians and reptiles have 3 chambers. All mammals, including humans, have 4. With each increase, blood and oxygen flows at higher concentrations. Tissues produce more energy. A higher level of activity is sustained. But how do toolkit genes fuel evolution's capacity to re-engineer a heart? To answer that, scientists turn to a vertebrate relative, a sea squirt.
So these sea squirts have a heart as well.
Yeah, they do have a heart that lies right there at the base of the adult. You can hardly see it, but you can see the gut. That's this orange area, and the heart just lies next to it.
Don't let the simplicity of that adult deceive you. That's our closest living relative. It's a close relative of the vertebrates, and it has quite a respectable heart underneath that goo.
Close to the gap.
The real action is once again in the embryo, when the sea squirt heart is first developing. And here, toolkit genes play a key role. When the animal is barely 100 cells, toolkit genes tell 2 cells in the tail to remain behind, and send another 2 cells migrating to the head to form heart muscle. Within a day, they start beating. During this process, sea squirt embryos sometimes make mistakes, and twice the number of cells start migrating to form a heart. When they do, it might make a heart with 2 chambers, resembling that of a fish. And this could be a way evolution works to make more complicated hearts, enhancing animal life. Thanks to endless genetic experimentation, vertebrates changed from lowly filter feeders like sea squirts into the world's top predators. And that capacity for experimentation is also built into the Spore game. So much so, it even surprises the developers.
Oh, that's great. Oh, that's great.
Well, that was awesome.
Every day you'll start up the game and see what people have made.
You're always surprised by the crazy stuff people wind up doing.
Of all the changes leading to the human body, the most significant may have come much more recently, when we shared the forests with our primate cousins. We're on the brink of locating the very genes that set us on an entirely new path. Computer game designer Will Wright is learning about the toolkit of genes that evolution uses to make and remake animal design.
Nature's designing creatures through genetics, and in the game Spore, we're letting players design creatures in our editor. Nature has a tremendous amount of leverage where, with very simple little things can generate these amazing, diverse creations. And in some sense, I want the players to feel the same thing.
Right now, the Spore team is debating how rigorously scientific they should be. Whether the game should be built so that a creature's eyesight evolves over time, from something that only detects light and dark, to an eye with fully formed optics.
And the idea is that every eye has got its own particular way of seeing the world. If you've got really bad eyes, we do this sort of distortion so that everything gets really blurry and vignetted around the corners.
But at the same time, the player's always going to start with low-level parts in the creature, which means they're always going to start with horrible vision.
Yeah.
Most people think their graphics card's broken.
Right, if they see this.
Yeah.
There's a concern that players may become impatient. Imagine if they had to wait 450 million years for eyes fit for a video game world. It wasn't until primates split off from mammals and monkeys evolved 50 million years ago that an altogether new arrangement of eyes emerged. Many mammals have 2 light receptors in their eyes. Scientists think the gene that makes them may have duplicated in some primates, adding a 3rd receptor. It's a small mutation with a big impact. Mammals with just 2 receptors see a bland, colorblind world. But when those redesigned monkeys now scanned the forest, looking for fruit or tasty leaves, they were equipped with full color vision. A genetic mutation gave them a leg up in the game of survival. Once our line of animals had a body plan, with parts like hands, hearts, and eyes, we were on the road to becoming human. Yet the final mile was the most impressive. A massive evolutionary leap from chimp to hominid. From quadrupedal to bipedal, hind legs lengthen, forelimbs and shoulders shrink. Knuckle-walking hands morph into precision manipulators. Fur-covered skin goes naked. The brain triples in size. All this, yet just a tiny change to the DNA. In chimps and humans, 98.8% of the DNA is identical. It's close, but that 1.2% must make the difference. And it's there that scientists are finding the particular genes that shifted our course from chimp to human. As our ancestors started moving upright, they stepped up to a more strenuous lifestyle. It's the moment we became hunters.
So as Eric's running, he's doing a number of things which are unique to humans. One of the set of features that makes him different from a chimp, that enables him to run that way, is that those tendons elongated in human evolution.
Scientists at Harvard want to find the key genes behind the ape-to-man makeover.
Why are we not chimps? First we became bipeds, and then later on we became runners, and we started sweating, and we changed our teeth. So it happened not all at once, in a series of steps. And so the trick is to find which genes changed when, so we can relate those genes to the fossil record.
Many different toolkit genes were probably involved. But the team is closing in on one, and it may have played a role in turning skin naked. Our primate cousins can only run so long before they must stop and pant, exhaling heat much like a dog. And that's because of their thick fur coats. Naked human skin has thinner hair and more sweat glands, allowing us to convey heat more effectively than any other mammal. Genes make skin repurposable. Recently, an ancient gene called EDAR, responsible for making scales on fish, turned up in the human genome sequences biologist Pardis Sabeti is analyzing.
I think it's quite powerful that the same set of genes that regulate scale in fish is, it's the same set of genes in humans that regulates hair, sweat, and teeth and under strong evolutionary pressure. It shows that there is a connection between them, and there are sort of common principles that guide evolution and genes that are adaptable.
Like the fin that's an ancestral version of our hand, our skin is the latest makeover of scales. And if the change allows the body to thermoregulate in the midst of intense physical activity, it's a crucial adaptation, perfect for hunting the big game. It can still be seen today. Kalahari Bushmen in southern Africa will hunt the kudu antelope without guns. Instead, they run, tracking and chasing the quarry relentlessly until it's too exhausted to continue.
As soon as you're on your hind legs, not only can you jog long distances after game and run them down as a new way of hunting, but you also have your hands free for manipulating your environment. You've changed the way you're dealing with your world.
Toolkit genes have augmented the body to the point where we start making our own toolkit, furthering the split from our primate past. As our kind ventured out to every possible environment, tools and technology increasingly made the difference. Yet none of this would have been possible without the evolutionary changes that increasingly chose brain over brawn. Nowhere is the difference between us and higher apes more profound than in brain power. But scientists have long wondered how evolution acted to increase cranial capacity by 3 times. Surprisingly, the key to how our brain developed may come down to a disease, one that is built into every human today.
When we first ran across it, we thought it was an artifact of our method of studying the structure of genes. But we realized that we all carry this mutation. Every member of the species Homo sapiens carries this mutation.
Dr. Hansel Stedman was searching for a cure for muscular dystrophy. While scanning the human genome, he found a mutation in a gene that makes myosin, the protein that builds muscle fibers. The mutation specifically targets the size and strength of a jaw muscle. But how are jaw muscles and brain size connected? In non-human primates, Like chimpanzees and macaques, the myosin gene is intact. No mutation. There's no question these animals have very strong jaw muscles, capable of delivering a powerful bite. And scanning the genomes of 7 primates confirms that none have the myosin mutation. The genes that built bite muscles have remained unchanged for millions of years, until us.
You can see that letter for letter, it's exactly the same until you get to this one place where it's like the tweezers went in and plucked out 2 bases of DNA only in humans.
The mutation causing a reduced jaw muscle may have opened up a new arrangement of the skull in early humans. There is limited real estate on the skull. It can house massive muscles on the outside or a big brain on the inside, but not both.
Most of the area surrounding the skull is muscle for closing the jaws. That's true as you cut right through this area of this gorilla skull. A little bit of brain there in the middle, all muscle surrounding it.
But a human skull is just the opposite, almost all brain, and only tiny holes on the edge for the reduced jaw muscles. Once the gene made smaller jaw muscles, it also slowed the fusing of the skull plates. In chimps, skull plates fuse shut at 3 years of age. In humans, the skull stays flexible for 30 years, in effect, allowing further brain growth. Strong jaw muscles and small brains were a feature of mammals for over 100 million years. From fossils, we knew that somehow the hominid jaw and brain had changed. Now, Hansel Stedman has found a possible explanation in the genes.
So I'm not saying that this mutation that shrinks this muscle up buys you Homo sapiens. All I'm saying is that shriveling up this muscle lifts an evolutionary constraint, allowing for continued brain growth that might otherwise have to stop.
Scientists are finding some of the first clues in the hunt for a human toolkit. A cluster of control genes working throughout evolution, ultimately coming together in human form. Like no other animal on the planet, we humans have evolved the capacity to explore our own origins. To look inside, down to the deepest levels of our assembly, and observe the machinery of life.
Oh man, that's great.
But just when we think we might be at the pinnacle, we're starting to learn we may not be. We're not the only creature evolution's toolkit has been designing. It's hard not seeing evolution as a ladder, and ourselves at the top rung. We often assume that humans are outfitted with the best parts in Mother Nature's garage. Yet the genetic toolkit is showing us that there's no end to the ingenuity of life. Much of it's still waiting for us to explore.
90% of the living space is in the ocean, and every major animal group is represented there. My main interests are in the ocean, because that's where you find the breadth of animal creativity. It's all there in the ocean.
Few get the chance to experience the abundance of non-human living things, as much as Tierney Teese, marine biologist and National Geographic emerging explorer.
When you look at humans, well, we're kind of boring for the most part. We've got arms and legs and that's about it. But when you look to the animal world, that's where we see incredible creativity.
That creativity will be put to the test.
We could do some gills on it as well.
With her knowledge of animal diversity and Spore's amazing creature animation, Tierney Teese and Will Wright are designing the ultimate animal.
That looks great.
How's that?
Their first issue is locomotion. When you can make your own super animal, why settle for just 2 arms and 2 legs?
I think we should have multiple legs.
Like how many?
Do you know about the echinoderms?
I've heard of them.
The
yeah.
sea stars and let's go to those.
Sea stars actually move on hundreds of legs.
They can go in any direction. They can lose an arm, grow another one, and they've got these incredible appendages called tube feet. And those tube feet, like a bucket brigade, will send the food to the center mouth.
It sounds like a city almost. We have like little road networks and this transportation infrastructure.
It is a little universe unto itself.
Remarkably, the same toolkit genes that are active in making tube feet in sea stars also build legs in flies, lobsters, and birds. Similar genes, vastly different animals. And when it comes to choosing a mouth, our imagination has nothing on nature.
Once you see this, you'll never think about abalone the same way.
Okay.
Okay, so here we're looking at the bottom side of an abalone. The shell is up here.
All right.
And this is the underneath. They've got that 1 foot, and this is the thing I want you to look at here.
Okay. Is this
Right
its
in
mouth?
there. This is its mouth.
Ooh, that's cool. Looks like some kind of mechanical
Buzzsaw.
grinder.
Yeah, and that's what we call radula.
An abalone's radula is another one of nature's brilliant and bizarre creations. An electron microscope view of their teeth shows why its mouth is so adept.
Metal teeth.
And they can scrape through metal even.
Oh, so it's like a bandsaw. It
It's
just
like
kind
a
of sits there and
bandsaw
grinds and
that
grinds and
zips
grinds.
and grinds.
Okay.
Amazing, amazing animal invention.
So I'm assuming you want one of these on your creature.
Absolutely.
And
The
where should it
radula is
go?
one of the most cool animal inventions out there. It's kind of a biologist's dream to be able to design your own animal. Oh my gosh, I love this. To pick and choose the traits of animal groups that you most enjoy. And it also helps put in perspective what it is that makes life, each animal group different. And why do some animals have this assemblage of characters where others don't? It's a great way of asking those big questions. Should we be able to fly? I think that's critical.
Okay.
Let's add a couple wings.
Having wings for us is kind of a problem unless we lose our arms, right? So we're basically, that route in evolution is cut off to us unless we were to readapt one of our current limbs.
That's true. I mean, and what's interesting is now we're starting to understand the genetic programming for making limbs and seeing what our limitations are and what our flexibilities are.
As creative as evolution is, species don't transform with the click of a mouse. Unlike Spore's creature making, there are limits to how far a body pattern can diverge. In other words, humans aren't about to start sprouting wings. For the moment. Yet we're on the verge of knowing what all the genetic nuts and bolts do. Perhaps we'll start directing our own evolution in ways we can only imagine.
You know, we are entering a brave new world where we can create devices which enhance our performance, robotic tools and so forth, but also manipulate our own DNA to change our bodies in important ways. And that, deciding how and when and what to do is really an ethical choice because the capability is certainly going to be here very shortly.
What we've accomplished is nothing short of amazing. We're on the brink of understanding the genetic machinery operating within evolution. A powerful new insight into the origin of species is revealing that all animals, despite their differences, share essentially the same genetic toolkit. That there are no such things as genes for worms, genes for flies, or genes for fish. Rather, the history of life is really the recycling and repurposing of ancient parts. That's our story too. An incredible journey connecting us to scores of related creatures, making their mark in every bit of our flesh and bone.